electrons is a cloud of electrons up on top. What would we expect to happen from this perfect 109.5 to creating a cloud up here on top of the nitrogen? Well, again, what happens? The electron cloud just takes a little more room, and it's going to push down the hydrogen. So I'm going to create a bond angle. It's a little greater in this direction than the 109.5. Therefore, it's pushing together the hydrogen a little. It's a little smaller than expected when we place a lone pair. Take a look at water. If water, central atom is oxygen here, what we end up with water is two unbonded pairs of electrons and two that are bonded. A perfect tetrahedron has 109.5, but now the two bond angles squish those hydrogen even closer together. The electron clouds simply take more room, and therefore they spread out and push together the hydrogens. So the 104.5 is the expected bond angle here. So here's what we've said. If I go back to this slide, 109.5 would be the bond angle when all are bonded. We then said it decreases to about 107 degrees if it's 3, 1 of a bonded pair. And if it's coming back here, if in water, taking this slide off and back to water, if two are bonded and two are non-bonded, we go to the bent geometry. 104.5 becomes this bond angle. Tetrahedrons have 4 electron domains. If all 4 are bonded equally, we get the expected bond angle of 109.5. If 3 of the 1 are bonded, it decreases slightly to 107. And if we have 2 to 2 bonding to non-bonding, it decreases a little more to 104.5. Again, the electron clouds taking up a little more room to spread out to create the least amount of repulsive forces. And that's what we've shown here. A derivative of trigonal planar geometry is the bent molecule. A derivative of the trigonal planar geometry is the bent molecule. If 2 of the 3 electron domains are bonded, 1 is non-bonded, we get a bent molecule. And the bond angle changes a little bit. So if I think about trigonal planar being bent, that means 2 are bonded and 1 is unbonded in terms of this particular shape. So sulfur dioxide has 3 different possible resonance structures. That's what they're showing you. Resonance between the 3 different molecules, 3 different possible correct answers of how to draw the Lewis dot structure. The bond angle is going to be a little less due to those electron clouds right up here. So if we predicted on our VSEPR chart that the trigonal planar was 120 degrees, if I have a lone pair of electrons, it's going to be a little less than 120 degrees between these attached borons. So again, the electron cloud expands, pushing down or pushing closer together for that electron domain, giving us a smaller than expected molecular geometry. Pyramidal and bent molecular geometries are derivatives of the tetrahedron electron geometry. When there are 4 electron groups, all 4 are bonded, we create a pyramidal shape. We can also have a bent shape, as I'm just reading through this slide. Here's what we're looking at, going back to the VSEPR chart I gave you. When we have a tetrahedron electron geometry, go to this chart. Here's all this slide is saying. If all 4 are bonded, the electron domain matches the molecular geometry, gives us an expected angle of 109.5. If 3 are bonded, 1 is not, we get an expected molecular geometry of trigonal pyramidal. A bond angle slightly smaller, about 107. And if 2 are bonded, 2 are not, we get a bent molecule with about a 104.5 bond angle as in a water molecule. There are 3 possible molecular geometries for the tetrahedral electron domain geometry. And that's what I'm looking at with this slide here. Here's a picture of a methane molecule. Perfectly symmetrical, we would call that a nonpolar molecule. Look up, look down, look left, look right. They're all equal hydrogens. A perfect molecular geometry of 109.5 for a bond angle. However, if we look at a tetrahedron for electron domain, still has 4 electron domains, but now I have a non-bonded pair, as in ammonia. NH3 is ammonia. Central atom has 3 hydrogens. Picture the electron cloud up on top pushing down a little bit. Instead of the predicted 109.5, this would have a little smaller bond angle between the hydrogens, closer to 107. This would be called the trigonal pyramidal shape. When 3 are bonded, 1 is not bonded, trigonal pyramidal. Same picture, different example. Arsenic in the center, fluorine around the outside. 3 fluorines attached back, but we have 1 lone pair. 4 electron domains, so the electron domain geometry is tetrahedral. But when 3 are bonded, 1 is not. The molecular geometry does not match. Tetrahedron for the electron domain, trigonal pyramidal for the molecular geometry, predicted bond angle about 107, smaller than the predicted 109.5. A second derivative of the tetrahedron could be a bent shape. And again, here's a water molecule showing 2 lone pairs of electrons with the connected hydrogens. The molecular geometry ends up bent. The electron domain geometry is tetrahedral. When I have 4 electron domains, 2 are bonded, 2 are not bonded, we have a bent molecule. Predicted bond angles, 104.5. Again, same picture, different example other than water. Here's chlorine hooked to 2 oxygen, carrying a -1 charge. This is a polyatomic ion called it's called chlorite. ClO2, -1 is chlorite. 4 electron domains, 2 are bonded, 2 are not bonded. We create a bent molecule. Expected bond angle, 104.5 between the oxygens. Because what I'm not seeing in this particular ball and stick model are the 2 electron domains that are not bonded. The VSEPR chart shows 4 electron domains, 2 bonded, 2 non-bonded. I can predict the bent shape. Derivatives of trigonal bipyramidal electron geometry. Here's what this slide is showing. One at a time. I can show all of this slide. You can read through it, but this is what it's looking like. Derivatives of the shape. Really is just showing the possible connections between those 5 electron domains. Trigonal bipyramidal. If all 5 are bonded, the molecular geometry matches the electron domain geometry. The derivatives take off a bonding pair. If only 4 of the 5 are bonded, leaving 1 non-bonded, the shape becomes a seesaw. Notice that the non-bonded pair is taken from the equatorial position. The second derivative, or possible molecular shape, of the 5 electron domains, 3 are bonded, 2 are not bonded. This is called T-shape. Again, taking off a second electron domain from the equatorial position. And the third possible derivative of the trigonal bipyramidal geometry is a 2 bonded, 3 non-bonded, giving us a linear. Notice that all 3 of those came from the equatorial position, so I can clearly see the axial position being left with 180 degrees for that bond angle between the top and bottom ligand. So here's what we're looking at. When 5 electron domains are present, but only 4 are bonded, 1 is not bonded, we get a seesaw shape. When the 5 electrons around the central atom have 2 lone pairs, we call it T-shaped. And if all 3 of the equatorial positions have been removed, we get what's called a linear.